all the excitement is in delta, so let's have a look. What is delta really? All right. In terms of field theory, we have defined delta already. It was K1 minus K2 dot R, like I just wrote on the last board, plus E1 minus E2. Okay, so that's our field theory delta. Now we're going for a more practical delta. There's a more practical version that's usually written because it's more relevant to an experimental situation where you're trying to really figure out what's contributing to the phase shift. Often when you have just two beams of light in a geometry, you don't think in terms of the wave vector. Right? So the more intuitive one is, let's see, here you got lambda naught down there. That's the vacuum wavelength. You have something delta path. Let me write that again. Where you can read it. Path plus delta phase times 2 pi. So the sum of delta path and delta phase over 2 pi, or times lambda, sorry, times 2 pi over the vacuum wavelength. This is actually equivalent to this. It's just different notation. So let's look at what these two new terms are. You know what the vacuum wavelength is. You know what 2 pi is. Let's look at these two things. So delta path is the difference in the optical path length. So the optical path length is kind of like how far the light goes, but in terms of counting cycles. So in air, where the refractive index is 1, then the optical path length is just the physical length. But if you go into another medium where, say, you go into glass where the index is higher, remember the wavelength goes down. So the optical path is always just the length times the index you're in. So if you're in air, then it's just the length that the light goes. If you're in glass, it's n times the distance, the path that the light goes. So we'll mess with optical path some as we get into more cases of interference. But this isn't the optical path length, it's the difference that the two waves have in optical path length. And we can actually show why you get this exact term, delta path over lambda naught times 2 pi, just by looking at it and making yet another approximation. We got to think about this angle right here. So the angle of each of the two position vectors, essentially, from the slit to point P with respect to the horizontal axis. We're going to assume they're the same. At the scale at which we've drawn this diagram, you can clearly see that R2 has a bigger angle, the lower one has a bigger angle than the upper one. But we're actually, remember, this is supposed to be really far away, this is supposed to be really close together. We actually assume they're pretty much at the same angle, and they're actually small angles, right? So if P is not too high, things are really far away, they're small angles. So what we can do is think about what would K1 minus K2 be. And I'm going to pull one switcheroo on you. I'm going to switch 1 and 2. Because I meant to say K2 minus K1. It doesn't matter. It's a negative sign. It doesn't make a difference. So there you go. R1 and R2 just changed places. So let's think about what that means. K1 minus K2 dot R. Well, that's equal to K1 dot R, or K1 dot R1 minus K2 dot R2. Right, so it's each one of these, and they both have their own k vector, each one of these plane waves times these two different r's. And well, then you say, well, if the angles are small, well, first of all, you can say that in each case, k is in the same direction as r. So you don't really need the dot products in this case. Right? So that's just part of the problem, k1 r1 minus k2 r2. And the difference in k's of these two plane waves is that they're going different directions, but we actually left that out of the problem. We have the r's and the k's in the same direction. So really the two k's are the same because they're the same wavelengths. Right? If you take the vector part away, it's just the wave number, and that's 2 pi over lambda. So they're the same wave number. So then you would say, well, those are both 2 pi over lambda and lambda naught since we're in air. Don't worry about it. Right? And so it's really just R1 minus R2. So, well, R1 minus R2 is basically just the difference in length between the two, right? So that's what we're calling delta path. So if we wanted to identify delta path in this drawing, it is, I've taken out a bunch of the little oscillating, or I've taken all the little wavelets so you could see better. But basically you would draw a line perpendicular right there, and that's R1 minus R2, right? It's just the difference in the length of this vector minus that vector. So you get left with this little piece right here. And let's see, if this is theta, if these two are both at theta, and one going from the middle is around theta, then this is also theta. So this length, this difference has a name. I'm going to erase this theta so that I can draw it real nice and neat. This distance, if you go through the geometry, is A sine theta, okay? Because you have a right triangle. The hypotenuse of the right triangle is A, the distance between the two. The normal to this ray is right there, and you want the distance from the lower slit to where the normal to that ray from that slit hits, and that's A sine theta, as you can see, opposite over hypotenuse. So that's this part right here. You can see, so 2 pi over lambda naught times the delta path, and in a minute we're going to show you the delta path is A sine theta. But let's first define delta phase. Right? Delta phase is the phase difference expressed in wavelengths, basically. So this one doesn't make a lot of sense. And well, actually, it's expressed in in wavelengths. Well, in distance. All right. Because what we're saying here is, say you have something that causes the two waves to be pi out of phase, right? A pi phase shift between the two waves. Well, to make this formula work, where you add these two path lengths, you have to say that's half a wavelength. So you would put 1/2 a lambda naught here. So you have 1/2 lambda naught here, lambda naught here. Those make a half, and it's half of 2 pi radians. So you end up with pi. Right, that's very complicated. The whole point is to get a phase. Why do we take a phase, turn it into a length, and then convert it back to a phase? I don't know. But this is the formula we always use. Okay, so you think of your phases as distances and then convert them. But the sort of the difference in path length and the difference in phase are kept up with that way. So now we can write delta for the Young's double slit, right? So it is the difference in path, and I got ahead of myself and defined the difference in path. It's A sine theta plus the difference in phase. Well, we know the whole point of this was that it's coherent. These two are coherent here. There's really nothing that happens to cause a difference in phase, so that's plus 0. We will have differences in phases on other problems, but for now it's 0. Over lambda naught, the vacuum wavelength, times 2 pi. Okay. So that's the delta condition, or the phase for Young's double slit. It's 2 pi A sine theta over lambda naught. The whole thing is done in air, so lambda naught or lambda is the same thing. Okay, and the next thing is to tie all that to the geometry.